Here's a transformer I just modified. Honestly, I didn't know quite how easy this would be to do this. I had a pretty bad record with a microwave oven transformer, so I kind of cringed on doing this. But it did work out okay. This is an 18 volt at 8 amp transformer, and I needed a couple extra volts out of it, so I got 4 more turns on it, and I get 23.47. It was 22 volts to start with, about a volt and a half. So I think that volt and a half is going to get magnified a little bit. If you multiply that up by 1.414, it comes up to like 2.1 volts. A pretty small amount, but that's really all I needed for the project here I've been working on. Kind of a weird thing here with this transformer. A while ago I did something really dumb, and this is a 4 amp fuse, AGC4. I shorted right across these two wires for, I don't know, probably all but 3 seconds maybe. The fuse never blew. There's some food for thought. Why would that be? Why would that be? Was it that 3 seconds really wasn't long enough for a fast-acting fuse? Or is there something happening with the flux density in these transformers that limits the amount of line current? Does it have to do with the magnetics of the transformer? Did the short across here not allow enough amperage on the primary to be drawn because of some magnetic properties with this? There's something to think about. So it could just be that the fuse, I didn't give it a half a second longer, or there could be some real science to magnetics. It's a bit ugly, but it's guaranteed to last. Everything's insulated pretty good. No wires are near the other ones. Was able to tuck them down there pretty good. It gets a bit frustrating feeding the wire through the core, and of course it wants to bind and skin on the sides of the transformer there, but I just pulled it through one of these holes and bent it over to hold the thing to keep it from unspringing. Right there's the wire, and then I brought a piece of number 16 around the other way to reinforce it and just epoxied the whole thing down. Kind of crude, but it does work. I'm not sure how that'll stick. Actually, you know what? It doesn't really matter if it doesn't stick the greatest in the world. This is a pretty old roll of cambric tape. 3M makes cream of the crop stuff, but it does kind of have a life expectancy to it. Yeah, it doesn't stick to epoxy, that's for sure. It should stick to that polyester tape down in there pretty darn good though. Just something to cover the ends up there. I found somebody on eBay that was selling some really good stuff. Real 3M Captain tape. That's something that's been hard for me to find, but I kind of hit the jackpot on this. Actually, it's not as thick as what I kind of anticipated it would be, but I think anything, especially a 3M product, is better than this worthless junk right here. If you see it on eBay, don't waste your time on it because you'll never get it off the roll. It's so thin. I don't know how well I'm going to be able to feed that through there. I did pull it off on the microwave oven transformer. There is kind of a method to the madness, I think. Got some tape around it. If you want to test your nerves, I'll tell you the way to do it right here. Take a piece of this, and we're going to cut it pretty short. If you cut it longer, you'll jump off a bridge. So you don't want to jump off a bridge. And then you very carefully stick the tape in no more than really 2 spots. And you see what happens. The tape just wants to go up against it and stick there. And if it's stuck the whole way up the length of the tape, when you shove this through, you will never in a trillion years be able to pull the wire back off the tape. This seems like it's probably a little bit more aggressive adhesive, which is a good thing, unless you're trying to do something stupid like this. But as far as the curl test goes, that's really the part that makes you lose your mind too. As soon as you pull the tape off the roll, pull it down and go to cut it, it just all curls back into a ball. And yeah, man, that stuff sticks to everything. So here's something pretty interesting about transformers. This was the transformer that I had in here before. This was the transformer I had in after that transformer. This is 18 volts at 8 amps. So that's what its ratings are. This is my new transformer. You see how this works. That is my new transformer, which is the modified version of this transformer that has the 4 additional turns on the secondary of it. Now the interesting thing about that is, this is the transformer before. I had 26 volts on it with no load, setting on the rectifier, and I had 22 volts on the rectifier with my 6 amp load on it. This is the Greek symbol delta, which just signifies change in math. So it was a change of 4 volts from load to no load. After I added the 4 turns onto it, I had 30 volts no load and 22 at my 6 amp load. So that's a delta of 8 volts. So now the voltage swing on the transformer is double what it was before by simply adding 4 additional turns onto it. Honestly, I needed to pick up 2 volts on this transformer, and I completely did that by adding the 4 turns to it. But, well, actually having a 30 volt ceiling on the collector of my pass transistor was something that was a little bit undesirable, and it was actually counterproductive to some extent to do that, because the whole reason I took out this transformer here was because the voltage ceiling was too high setting on the collector of the pass transistor. Thus it was dropping a higher amount of power onto the transistor, and more power equals heat on the heatsink. So the whole experiment was slightly counterproductive. I did achieve what I wanted to achieve, but if you look at it from this aspect, this was kind of the clincher here in this case. I need to power 24 volt stuff from the rectifier. And you might look at that and say, well, you got 22 volts there. How can you do that? Well, the 24 volt things that I'm powering will run just fine and dandy at 22 volts. Actually, I think they would have probably ran fine and dandy too at 20 volts, but 22 is closer to 24. However, the problem comes into play when you're calculating the dropping resistor to put on that. Because of course, if you're powering something that runs on 24 volts off of here, putting a dropper resistor on it to make it run at 22 is somewhat counterproductive, because you're just going to lower the voltage even further, and it's low to start with. But you have to put the dropper on because 26 may be too much for it. You see what I'm getting at? It's kind of a yo-yo. And in the case of this transformer here, it really wasn't that bad. But adding the 4 additional turns just upped the ante to the 8 volt swing on it. So now 30 volts is too much for something that I'm powering that needs 24, and 22 is still 2 volts too low. But if you put the dropper on to make it pretty decent at 30 volts, then you really run into problems, because now it's dropping this, what used to be 22, probably down to 20 or 19. You see what I'm getting at? It's a little bit of a counterproductive yo-yo there. But I can make this work. It was more than I really expected. This load resistor here is extremely close to what my load on the high voltage tower is going to put onto this power supply. So I don't care that the voltage sags a little bit under load. This is kind of a crude regulator here, but the reason I did that is because these regulators here aren't prone to blowing up because they got some high voltage on them. So all I need is 16.6 volts at about 6 amps. And that's pretty close to where we're at there. Now, if I turn the voltage the whole way up without a load on it, it will jump up to 18. But my high voltage tower will pull it down. So one way of looking at this is that this power supply is matched very, very well to my high voltage tower, meaning that it can just supply enough current to it and probably slightly more. It's always nice, at least in most cases, to have a lot of headroom on a power supply, but sometimes it's not really such a good idea because if the circuit malfunctions or something like that, you can end up delivering a lot more current to it in the failure and have things go into smoke on you. But in the case of this here, the transformer just does what I need it to do, and that's about it. So if there was a failure in the oscillator, the transformer itself would be the current limiting. So there we go, 16.6 volts at 6 amps. Kind of back to what I was saying before about the reason why I took this big hogging satellite transformer out of there, about it setting too much voltage on the pass transistor. When you run these power supplies at reduced voltage, you're going to get a lot more heat on the pass transistors. So if I jack this voltage down to about 10 volts or so there, the lower you go, the worse it's going to get. Put a load on it, roughly 3.5 amps. The pass transistor is actually dissipating much more power than what it was previously, even though the current consumption or the current on the load is much smaller. You might not think that, but that's how it works. The lower I turn this, the hotter that pass transistor is going to get. If I put a smaller load on it, like here, where it's 2 amps, the power dissipation is going to drop down. So it's slightly warm there. It's only a 2 amp load on it. But if I juice it up here a bit, it'll run even warmer now. It's generating a bit of heat now. Not much, but more than what it was, that's for sure. So anyway, there's something to think about if you want to stack some additional turns on the transformer. It may end up not being worth the trouble that you went through to do it in some cases, I would imagine. But in this case here, everything worked out fine. It was productive, but it wasn't as productive as I had hoped for by changing to these transformers here. So anyway, hey, thanks for watching my video. You take care and have a great day.